Hi Jayla, so believe it or not, I have only about a month left of class this term, and so that is frightening. So all I could think of doing a vlog topic this week was on stuff I'm studying. I'm going to try to explain to you the basis of inverse theory. Now stick with me, maybe we can make this through this and you can learn something and then impress people. I'm just trying to help you guys impress people with random knowledge. So inverse theory. I will give you the formal definition that won't make sense and is a lot of words, but it's always good to start out with formal definitions of things, right? So inverse theory is an estimation of parameters of a postulated model for a physical system from observations of some process that interacts with the system. Sound fancy, huh? What a model is an idealization of a system. So yeah, it will make sense. Let me just keep talking. If not, leave questions down below. Maybe I can answer them. Probably not. Yeah. Yay. Okay, so before I talk really about inverse problems, let's talk about forward problems. And now forward problems are pretty much the class I took in the fall. And I thought that was a little challenging. So in a forward problem, you're given a model and you compute the data. So you're given a set of parameters, you run it through the system, and you get your data. Now, the thing that's cool about forward problems is that nature is pretty much a forward problem. So in nature, you have a set of inputs to a system, and then you get outputs. And you can measure those outputs, and that's pretty much what most of physical science is. Nature is very well behaved because, you know, there's things like laws. The solutions usually exist, and they are unique, meaning there's only one solution. So basically you input the parameters. Those parameters are only going to lead to one solution. They're not going to lead to like more than one, because that wouldn't make sense if you were to run it through that model. The cool thing about forward problems also is they're stable. So you can have small changes in the model and your data won't be changed much either if it is representing the system correctly. But now we move to inverse problems, which is my current class that I'm taking. And so in inverse problems, you're given a data set, and from that data set you need to compute the model. Now this is extremely more difficult. The thing is that inverse problems are not physical, natural problems. They are mathematical problems. And that means they're not very well behaved, and because of that, it means more fun math. Solutions may or may not exist, and they're generally non-unique, which means one set of data can be from a infinite number of models. Also, this kind of problem is also unstable, which means you change the data just a little bit and the model is going to change greatly. So that is not very fun to work with, but it can be useful in geophysical problems such as determining the structure of the Earth. Inverse problems are mainly used in places you can't go and study it physically, because we can't just drill down into the Earth to see how it is. We have to go about it by other ways, and by highly mathematical ways. And that's how we can figure out, by sending seismic waves down and seeing how they are reflected and such. So yes, that is somewhat of an introduction to inverse theories. So it gets a lot more complicated, if that wasn't complicated enough. It's useful though, hopefully, one day. So I hope you learned something, and bye!